So I've got to the stage where we've shown that the Sippel's experiment strongly contradicted the theory of rational behaviour that neoclassical economists love, this idea of completeness, transitivity, non-satiation and convexity. But you all thought they were reasonable to begin with. Let's go backwards now and take a better look at them. How about completeness? That's the one you all started with, and that says that given any two bundles, like two shopping trolleys, you can tell which one you prefer, and you all thought that was okay. And it does sound okay when you see it in the way the economists present it, with biscuits on the vertical axis and bananas on the horizontal. Two things to look at, two commodities to consider. You might have 4 biscuits in one, 4 bananas in the other. There may be about 100 combinations. Now, one thing I want to point out to you, by the way, is every other time you've seen a set of indifference curves, I very much doubt you've ever seen numbers on the graph of any sort. Okay? So I'm going to whack some numbers there and see what it implies. So let's say we've got between 0 and 10 biscuits and between 0 and 10 bananas, which means you've got about 100 different combinations you could actually buy. Now, some of those combinations you'd ignore because they're either far too cheap or far too expensive, given your budget. But others, you can't. They're too close to what your budget line is. So in that case, there's about 10 different pairs you've got to look at, which means you've got to do 10 budget calculations and make 10 utility comparisons. No problem. But what about if I want to shop for something other than biscuits and bananas? Let's say you whack Mars bars on there or milk. How do I handle that? What do I do? Another axis, exactly. I've got to draw another axis. And when I do that, every other commodity, therefore, is another dimension to the problem you're looking at of what do you buy when you go shopping. Now, if you only have 10 units of each, then if there's 2 commodities, you've only got 2 axes and therefore 100 combinations. But if you have 3, there's 1,000. If you have 4, there's 10,000. How many in Sippel's experiment? Well, he had 8 commodities, so there's 8 dimensions. And he gave the students unlimited range they could choose. They wanted 362 millilitres of Coke. That's what they could get. Okay? Well, let's make it simple. That gives you an infinite number of choices. Let's make it simple and say there's just 5 combinations of each. So you could have 0, 15, 30, 45 or 60 minutes of video. That gives you 5 to the power of 8 combinations. How many is that? Anybody not looking at their sheet can tell me? Good. It's a lot. It's almost 400,000 different combinations. Now, to go back to my shopping trolley illustration, that's 400,000 shopping trolleys. Okay? That's 400 by, that's what, about 600 by, between about 650 shopping trolleys that way and 650 that way, each with a different amount in them. Do you reckon you can pick the one you like the most given a certain budget? Not so easy, is it? Okay? Completeness is one of these abstract ideas that sound okay on a sheet of paper. But when you actually look at it and see just what does it actually involve, it rapidly ends up with an astronomical number of different combinations. And therefore, for you to be able to definitively say you prefer a combination, with 15 minutes of video, 25 minutes of playing a game, a cup of coffee, 2 pretzels and something else, to another one with slightly different numbers, only if it's really extreme. Only videos in one, only coffee in another. At those extremes you can say something. But in the middle, it's just impossible. You can't differentiate that finely. Not only does your mind not do it, the calculations involved, even if your mind had a model like that inside it, are simply impossible. Now, your real preference is rational, to work out which of those 400,000 you prefer given a certain budget. But the reality is a bewildering array of choice. And I want to show you just how bewildering that array can become. So it's not, the difficulty isn't in finding the optimum combination, which is what economics says is rational behaviour. The difficulty is making a sensible decision in finite time. Now consider going shopping. And if you go, from what I've been told by people who work in supermarkets, there's between 10 and 100,000 different items in any supermarket, average supermarket. But I'm going to say, let's just imagine we could break it down into 100 different classifications. So forget about skim milk versus light, we've just got milk. Forget about dark chocolate versus light chocolate, it's just chocolate. Let's say you broke it down to 100 different combinations. That'd be an incredible act of simplifying the choice when you walk inside a supermarket. And all you're going to decide is whether you do or don't buy one item of each. So how many combinations do you reckon that gives you? A real lot would do. 2 to the raised to the power of 100 is that number. It took me a while to work out what it was verbally. That's 1 million trillion different combinations. So we're not talking, conceivable number of shopping trolleys like 400,000 now. We're talking 1 million trillion. Now that means that number of shopping trolleys, to give you an idea of how many combinations that implies, it's 1,000 billion shopping trolleys that way. Would you reckon that would make it to Perth? Imagine it would. And 1,000 billion that way, and 1 million of those combinations. You'd probably be able to cover the planet, maybe even Jupiter, the surface of Jupiter, at a guess, with that many trolleys. And that's just going inside a shopping trip, we're looking at 100 items. It ain't so rational to think that a rational person has a complete set of preferences anymore. It's simply impossible. So it's a toy model. Looks good on paper, but it can't possibly scale to reality. And that's because, technically speaking now, talking from a point of view of a computer programmer, consumption is what they call a problem with exponential complexity, and that is the number of combinations you have to consider rises exponentially as you increase the number of commodities. With 2 commodities, it's pretty simple. 2 to the 2, if you're making a choice, do or don't I buy those commodities, that's easy. But 2 to the 100, simply impossible. So the fact that it scales exponentially makes it impossible, even for the most sophisticated, powerful computer on the planet or in the universe, to explain the problem. So imagine you've got a computer and you programmed it so it had your utility function inside there. So it actually had a complete mathematical specification of all your tastes and preferences. And you then said, let's get the computer program to work it out for me. Imagine it took that computer 10 millionth of a second to work out the ranking of 2 different combinations, which is pretty fast. How long would it take to go shopping? Well, it depends exponentially on the number of products you're looking at. So given a computer that can make calculations that rapidly, one utility comparison every 10 millionth of a second, it would take that computer program a very tiny amount of time to work out what to do with 10 commodities, but you get up to 50, it'd take it 3.5 years. So hiring a computer doesn't particularly help. Now, I often get told by neoclassical economists when I put this forward, they say, well, that's reducing humans' really sophisticated brain to something as simple as a computer, and obviously we're brighter than that, and there's more to, the brain can do better than that. Well, as one of my students, my PhD, Sona Technicolor down here in the front row, by the way, University of Metal and Electrical Engineering, doing work on applying neural networks to economics. So Sona knows a bit about the brain and a bit how it functions. Grill him over a coffee later. The brain has roughly 10 to the 11 neurons. Now, that's 100 billion neurons. Is that right, Sona? Yeah. Okay, 100 billion neurons. And each neuron connects to about 1,000 other neurons, which is a fairly high level of connectivity. And signalling between those neurons is a large part of what thinking actually is. We're still learning a lot more about it, but that's the basic idea of signalling. And those signals are transferred by voltage spikes, which are actually communicated by pumping, I think is it a potassium ion? Yes. A potassium ion which carries a positive charge along that, physically along a dendrite into the neural part of the neuron, and then out along an axon. And that takes about 1 millisecond, 1,000th of a second to generate a spike, which is a bit like 1 bit of data, not a byte, a bit of data being sent from one register to another. And there might be 100 or so calculations like that by the brain to generate one response. Now, when we take a look at how fast people actually make perceptions, it tends to take between 1/20th and 1/10th of a second for people to recognise something. So if you think you're a really hotshot car driver, and you can, floor the accelerator as soon as the lights change, it'll take you between 1/10 and 1/20 of a second to actually start going after the lights change. And ditto going shopping. Okay? Now 100 perceptions like that might take you 5 seconds. So what I'm now saying is, let's imagine the brain actually operates as a massively parallel human computer revealed preference system. So the neurons pack together and a bunch of them work out what you prefer, and that's all the brain does, which it doesn't, of course. And if every decision took 5 seconds, then that human computer would operate at 5 by 10 to the minus 11. That's a lot faster than the 10 to the minus 7 I showed beforehand. So maybe that solves the problem. How long would it take to go shopping? Well, given exactly the same problem of shopping for 50, rather than taking 3.5 years, it'd take 40 minutes, which is pretty much how long you take to go shopping, I imagine, when you go to a supermarket. Pretty much 30, 40 minutes?
That's just for the thinking.
Pardon?
That's just for the thinking, right? Not for the actual walking.
Oh, yeah, well, that's different, yeah. Well, let's extend it a bit and say, what if you look beyond 50? What happens then? Say 100. Oh dear. To work out with that massively fast computer the decision of whether to buy or not buy one item in a 100 commodity store would take you 80 billion years. That's 6 times the age of the universe. Okay? That's what happens with an exponential problem. You simply can't solve it by throwing more computing power at it. And that's one reason, for example, your passwords work reasonably, to block other people from getting access to your data on the internet, because solving that problem is another problem of exponential complexity, and that's why we can use simple passwords to block our data from other people. Okay? Now shopping fits in the same category. You simply saying you can actually solve the problem by throwing more computing power at it is like saying you can crack any passcode just by taking a longer time. Yeah, you can, if you can wait 80 billion years to break into somebody's bank account. I think by that stage you might have starved to death. So any problem like this can't be solved by computing power. It scales, in this case, 1 plus the number of units bought, raised to the power of the number of commodities. 2 to the 50 is 10 million billion combinations. 2 to the 100 is just even beyond that, unbelievably so. They're inherently non-computable. So our definition of rational behaviour is simply impossible to apply either for a human being, as is seen from Sippel's experiment, or for a computer when you take a look at the actual processing involved. So the type of behaviour that economists think are rational, which is finding the optimum outcome for something, is only possible for computing programs and problems that follow what they call polynomial complexity. And that's where the problem, rather than scaling by something to a power, scales by something squared or something cubed. Okay? It doesn't go beyond that. So we have a number of choices raised to the power of a number of commodities, can't solve it. But other problems where it's polynomial can. Now, one of the examples of that, does anybody do computer programming here? A few, that's good. Okay. One of the commonest things you have to do is sort a list. And one of the simplest algorithms to do that on a computer is called the bubble sort. And that simply finds like the bottom number in a list of randomly sorted numbers, compares it to the one above, and if it's smaller than the one above, you move it up the list. That's the basic idea of the algorithm. Now, that then lets you sort a number, take a list of numbers which are not in numerical order, like at the top of the list there, and sort them to the stage where they are. So you bubble sort and then you split, and on you go. And in that illustration there, I've got 3782521954. The computer program applying a bubble sort to turn that round to 1 to 9 in the correct order takes 34 steps. Now, if I add the number of the worst case, of course, is where there's I've got to say get it into 1 to 9 order, and I give it in 9 to 1 order. It'll take 100 steps to get there. If I gave it 1,000, it'll take 1,000,000 steps. If I give it 1,000,000, it'll take 1,000 billion steps. That's a lot, but it's nothing like the number of steps involved when I scale the number of commodities to buy. I didn't even get to 1,000 commodities. The number, if I put up the number of 2 to the 1,000, the computer screen wouldn't be big enough to show that number in the normal decimal print you're used to. So that's scalable. It's feasible to throw that at a computer and say, if you can't do it with this many processors I'll whack in a couple of extra processes. So the average case for this type of problem is n times the log of n, and that means that if there's 10 items, it'll take 10 steps, because that's 10 times the log of 10, which is 1. If there's 1,000, it'll take 3,000 steps. If there's 1,000,000, it'll take 6,000,000 steps. It'll get there. So that's easy, that's doable, that's the sort of thing you can rationally decide the optimum outcome on. But in the sort of stuff we're looking at in economics, even shopping, it simply isn't possible. Because if I then take a look at the comparison working, say, to billion comparisons a second now, the amount of time it would take to go shopping when you're looking at one or more items, or two or three items, would take more than the age of the universe multiplied by the age of the universe. Okay? So it's an irrational definition of rational behaviour. The theory completely falls over, and it's no wonder it doesn't work. So we can't use that as a basis for actual behaviour, because the capacity to compare bundles just doesn't exist. You can't do it in a finite time, and all the other axioms can collapse. Once you can't do it at the completeness level, then the odds you're going to have transitive choices are zero. You'll find a few cases where that'll happen, but that'll be luck. Non-satiation will probably also disappear. Convexity's out the window. So they're all breached. But the thing is, we all manage to shop. So what are we doing that's actually rational? We've got to redefine what rational is now. And that pretty much is satisficing behaviour. You choose a satisfactory bundle. And you do it in all sorts of ways. You set priorities. Priority 1, make sure you buy the toilet paper. Okay? You get the most important or desirable item first off the list. Habit, get that muesli we bought last time. Okay? Categorise, don't forget to get some cheese, etc., etc. And that's what we tend to do. We purchase within categories, and when we're doing that, we're drastically reducing the number of dimensions we need to consider. And therefore you can go to a supermarket which contains 10,000 commodities, finish the shopping in 40 minutes, including picking the items up, rather than just deciding what to buy, and walk out in finite time. Okay? That's rational behaviour. So the complexity of computing, however you define computing, however you treat the human brain, overwhelms what economists think is rational behaviour, which is optimising. And we find much more sense in non-economics disciplines than you find in economics about it. This is taken from an introduction to a book called The Theory of Natural Computation. And again, a bit of what Sonner's doing in his PhD comes in here. Computer scientists have now built all sorts of algorithms to solve all sorts of problems. They're saying, well, the brain doesn't work that way, we've realised. It does other things, so maybe we should ape the brain to work out various problems and find a way of aping the structure of the brain in computer programming. Now, in doing this, they still say you've got to be obeying some laws of computation, and this is the way they state the laws of computation. And take a look at this compared to the way economists state laws. Economists give you, like, tablets from Moses, where thou shalt do the following thing, sort of stuff. This is how they define the laws of computing. The first law is you cannot compute nearly all the things you want to compute. Now, I haven't shown you that, but it's been proven in mathematics that most problems can't be solved. If you did the courses I'd make sure you did if you're doing economics the right way, the way I think it should be done, you do differential equations as one of your subjects. And very early on you'd learn that most problems in differential equations cannot be solved. The problems they give you as exercises to do are specifically chosen so they can be solved. It's quite simple to derive a differential equation with very little complexity to it, which there is no solution. The second law is the things you can compute are too expensive to compute. And that's what I've shown you. Even though you could solve that problem, the computing power you'd need exceeds the size of the universe. So it's not going to happen. So therefore you've got to work within those constraints. And that's the way that computer scientists work. You've learned a lot more about human behaviour by studying computing than you will by studying economics. So exact optimal answers are simply impossible to achieve. So revealed preference is out the window. As a description of human behaviour, it simply doesn't work. Normal behaviour must violate those axioms because the actual behaviour is computationally impossible. And therefore true rational behaviour is making a satisfactory choice in finite time. goodbye a large part of what you've been taught of how to model human behaviour. But it gets worse, because even if revealed preference did work, and even if every last one of you had proper downward sloping Hicksian compensated demand curves, even if I got that, the market demand curve can have any shape at all. And you haven't been taught that one. I actually gave a lecture on another topic at the Economist conference recently. Had about 100 people in the room, quite a few professors of economics, lots of lecturers, a few PhD students. I asked how many of them knew of what are called the Sonnenschein, Mantell, de Breuer conditions. And the answer was 2 of them did. They were the other 2 presenters, both critics of economic theory. Now this should be taught. It throws away the downward sloping demand curve. You can't get it. So even if you start from individuals with those downward sloping demand curves, you can't derive a downward sloping market demand curve. And we'll go through why in the next lecture. That's it for the lecture. You want to hang around for a chat? Let's do that.